Hi, my name is Rohit Pasula, and this is my video for Lab 5, Faraday's Law. The objective of the lab is essentially to collect observational data of a magnet falling through a conductive tube of aluminum foil. Afterwards, we will model the magnet interaction computationally through a program called GlowScript. The fundamental principle demonstrated throughout the lab is Faraday's Law and Lenz's Law. Before going through the procedure of the lab, there are a set of assumptions that we must assume. First of all, we are going to assume that the magnet models a magnetic dipole. Similarly, we will also assume that the aluminum foil models a tube that the magnet will fall through. We will consider air resistance to be negligible in this experiment. Therefore, we can assume that gravity and the magnetic force from the aluminum foil are the only forces acting on the falling magnet. Now, the procedure of the lab includes a phone, magnet, and an aluminum foil. Using a phone, mark the north pole of the magnet. Set up a camera and record the drop of the magnet through the aluminum tube 5 times. Determine the average of the times of the 5 drops. The data recorded is to the right. The average time for all 5 drops was 1.26 seconds. Now, the checkpoint questions. Why can't we use a ferrous tube? For example, a steel pipe. A ferrous tube would consist of iron and would as a result act as an induced magnet and interfere with the falling magnet. Now, what happens to the magnet? How does this compare to a magnet falling in free space without a tube? Well, the magnet falls much slower than if it was to fall in free space without a tube. This is due to the magnetic force of the aluminum tube. Creating our computational code, we first set up the initial conditions, including the geometry of the tube and the magnetic moment of the bar magnet. Then, we calculated the magnetic field at a position r relative to the bar magnet and calculated the rate of change in the magnetic flux through each ring caused by the falling magnet. Lastly, we utilized Faraday's law, Biot-Savart's law, and Newton's third and second law to create a simulation loop of the bar magnet. So as you can see, the model generated is to the right. The model shown is a visual representation of the bar magnet falling through the tube. The computational time was approximately 1.32 seconds. Now, there are some possible sources of error that may have occurred during the course of this experiment. One is that other electronic devices in my surroundings may have affected the results. Human error in measuring and recording the magnetic field components could have happened as well. Inaccuracy in orienting the experiment to compensate for magnetic north due to human error again is plausible too, as well as the human error in determining the time for a recording. So, for our reflection questions, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity of the conductor was reduced as close as possible to 0, the current would be significantly larger. This would cause the magnet to fall much longer through the aluminum tube. Now, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Cutting holes or slots in the tube would decrease the number of ring segments. This in turn would decrease the induced current and magnetic force. As a result, the time that it would take for the magnet to drop would decrease as well. Thank you for listening and have a great day.